Hello everyone, I am Paolo Pedinotti from the University of Pisa, Italy, and in this video I will present the work Did the Cat Drink the Coffee? Challenging Transformers with Generalized Event Knowledge. This is work done in collaboration with Giulia Rambelli, Emmanuele Chersoni, Enrico Santus, Alessandro Lenci and Philippe Blache. It has been shown that Transformers language models such as BERT possess word knowledge to a certain extent. But do they organize and use this knowledge as we humans do? To answer this question, we focused on the notion of GEK, which is an acronym for Generalized Event Knowledge. This notion summarizes a range of psycholinguistic evidence that our conceptual knowledge is organized around abstract and prototypical representations of free-word event participants and their interactions. This knowledge is used to distinguish typical situations from atypical ones. The two key properties of GEK are that it is generalized and compositional. By generalized, it is meant that representation abstract over the prototypical characteristics of specific event instances, allowing for a quick estimation of the typicality of novel events. For example, we can quickly conclude that both an airplane and a helicopter are likely to fly because the two entities possess prototypical characteristics of flying entities. Compositionality refers to our ability to make judgments about the plausibility of specific events by combining different pieces of knowledge. For example, we know that coffee is a typical patient of the event drink, but we also know that this does not hold when the agent of the event is a cat. To investigate if computational models, and specifically transformer-based ones, encode specific knowledge, we tested them on the thematic fit task. Given an event, a candidate filler, and a semantic role, the task consists in assessing how much the filler is likely to occur in that particular role. We used the data created by Vasallo and colleagues, a collection of 663 pairs of events annotated for typicality, with each pair containing a typical event and another event which is analogous to the first except for one participant that makes it atypical. For a better assessment of the abilities of the transformers, we compared them with the structured distributional model by Chersoni and colleagues, a model that incorporates intuitions from previous distributional approaches to event knowledge. SDM models explicitly the abstract nature of event knowledge by integrating a graph representation of events with word embeddings. It also comes with an algorithm to model compositionality. To get an estimate of how much a transformer considers a given event as typical, we adopted the fill-in-the-gap probe approach. We converted the event tuples in fit in sentences and we masked the candidate filler, with probabilities asked to the model. We experimented with 4 different transformers different for category, architecture, size of the training corpus, and training objective. In our main experiment, we evaluated the models by simply computing the Sperman correlation between their scores and the human typicality ratings for all the events included in the fit. The table shows that the correlation scores are quite high for all models and all event categories in the data, and transformers generally outperform the distributional-based model. We also observed that the performances of transformer models are generally very similar and the best model depends on the subset of data considered. This is surprising given that the amount of data used for training varies considerably across models. Moreover, the difference in performance between transformers and the distributional baseline is significant only in one case, even though the structured distributional model learns events from a corpus whose size is comparable only to BERT, and by design the model suffers from data sparsity. This evidence suggests that implicitly learning from more data does not necessarily ensure a more successful acquisition of the knowledge targeted in our dataset, and the incorporation of explicit mechanisms to organize and combine the knowledge learned from data can facilitate the task. Despite the encouraging results, we felt that the correlation score alone was not adequate evidence to answer our original question. In fact, the lack of control over the characteristics of the items makes it impossible to estimate which aspects are acquired from the models and which are not. We therefore decided to perform 4 additional experiments where we use diagnostic datasets, small set of items that are manually created to test whether the models possess specific abilities. Our first additional experiment was intended to study the aspect of compositionality. In the table, we report some cases in which BERT-based assigns a higher probability to the atypical event than to the typical one. These examples raise some doubts that the model consistently combines knowledge from different cues. As you can see, the model's predictions are based on the knowledge associated with only one of the context words, namely the verb. For example, the model predicts that the event "the mason mixed the soup" is more likely than "the mason mixed the cement," and "the climber climbed the staircase" is more likely than "the climber climbed the rock." Trying to identify factors preventing the model from integrating knowledge from different words led us to hypothesize that the model tends to use only knowledge from the local context when it is particularly informative, that is, it strongly cues certain events. To test this hypothesis, we selected 31 pairs of events from DT-Fit and we replaced the atypical filler with another atypical filler from the words with the highest local mutual information with the verb in the Wikipedia corpus. For example, album is highly associated with the verb release, but the event "the terrorists released the album" is clearly atypical. Our results show that BERT is generally robust to this manipulation of the data, but makes some errors. It is difficult to find a common explanation for the errors, but we observe that the atypical events that BERT classifies wrongly are more plausible than the other atypical events, thus suggesting that the model still considers the world context when making its predictions. In the other 3 additional experiments, we focused on whether transformers make and use abstractions in a way similar to humans. We argued that DT-Fit, as well as other datasets used for the thematic fit task, is partially inadequate to test this aspect of knowledge, because it is not designed specifically to examine how the models classify novel, infrequent events. We adopted 2 different strategies to disentangle the concept of typicality from the concept of frequency. In the second additional experiment, we measured the accuracy of transformers on the physical possibility task, using the same methodology of the main experiment of 616 pairs from the dataset created by Wang and colleagues. The task consists in distinguishing events that are rare but nonetheless plausible due to the physical properties of their participants, like the ant sees the pin, from events that are rare and even implausible, such as the ant sees the car. The nature of the task gives us control over frequency and forces the models to use reasoning processes involving generalizations. We observe a decrease in accuracy with respect to DT-Fit for all transformers, which we attributed to 2 causes. On one hand, the models trained on text-like transformers do not learn physical properties of objects that are crucial to make the correct judgments. On the other hand, models do not use their common sense knowledge in the same way as we do. The second strategy that we adopted consists in testing transformers on examples that the model probably have encountered rarely during training, but that we can easily classify as typical event instances by applying generalizations that are natural for us. The first generalization that we tested is based on the semantic features of event participants. If the models abstract prototypical representations of event participants, they should classify several candidate participants as equally typical, provided that they possess the semantic features required and irrespective of their frequency. To determine if this is the case, we measure BERT accuracy on a set of 39 event pairs from DT-Fit, where we replaced the typical filler with a synonym that has low frequency in Wikipedia. For example, from the event "the veterinarian examined the dog," we obtained the equally typical event "the veterinarian examined the puppy," which we expect to receive a higher score than the typical counterpart "the veterinarian examined the plant." Surprisingly, we found that BERT accuracy drops to random level for this dataset, which we interpreted as evidence that the model misses the generalization and relies exclusively on the probability of a given word combination. A similar conclusion can be drawn from our last additional experiment, where we tested the generalization based on the semantic relation between event participants. We started from the assumption that a model should classify a given event as typical or atypical independently from the order in which the event participants are expressed, provided that semantic and syntactic relations between participants are maintained. We tested the Roberta large model using the same method and evaluation measure as in the main experiment, but this time we converted the event tuples into sentences characterized by non-canonical word order, using the interrogative and the cleft constructions. We found that, on cleft sentences, correlation between human ratings and the model's scores significantly decreases for 3 out of 5 event types, indicating that the model does not always use heuristics based on linguistic structure, as we do. Returning to our original question, the results of our experiment indicate that transformers acquire mechanisms to compose knowledge associated with different words, but consistently show that the models do not make and use generalizations in the same way as we do. Our results also suggest that testing the models on examples that can be solved only by using human-like processes can provide a more detailed picture of the model's abilities and standard evaluation, paving the way for future improvements. We therefore suggest two future directions for computational research of event knowledge. First, the creation of a larger human-annotated benchmark explicitly designed to test the generalization abilities of the models. Possible strategies for its creation are a careful choice of the events included, aimed at decorrelating frequency and typicality, and annotation with explicit information such as the semantic features of the prototypical event participants. Second, the development of techniques to improve the generalization abilities of language models with respect to event knowledge, such as fine-tuning or related tasks. As shown by the comparison with the distributional baseline, modeling these mechanisms could improve the model sample efficiency. Thanks for watching this video. If you have any questions or ideas for future work, please join the online conference or feel free to reach out to us.